So if you stick something on the wall, right, this track here, so you can assume that the wheels here are glued to this wall. So why is this track not falling? Looking at the free body diagram. Hi there. So now this is then the object now attached to this wall. So it's attached by glue here. So the free body diagram looks like this. So you have the force of gravity acting on this wall. So if this glue was to stop working, this wall was this object here was going to fall down, right? So this glue here is allowing this object to stay like this, meaning that there is a force opposing this force of gravity. So it's difficult to sort of visualize how there can be a force that is acting upwards when this glue is sticking to this wall here, right? So to better understand this, we look at the inclined wall. We look at the inclined plane, I mean. So the inclined plane has an angle of inclination, right? Which makes this object here to have two components of force of gravity, the perpendicular component and the parallel component. The parallel component has sine theta and the perpendicular component has cos theta. So the free body diagram looks something like this. So you have the normal force. The normal force will be acting perpendicularly upwards like that, and then you have now the perpendicular component of the force of gravity, and you have the parallel component of the force of gravity, and then you have the force of friction caused by the inclined wall. And all of these forces are equal because of this object is not moving. So you can imagine that this object is just placed on the inclined and there is no glue sticking here. So as you start to increase this inclined wall here, the force of gravity, the frictional force, because the frictional force is given by mu mg cos theta. So mg is the force of gravity and mu is the friction variable. And then this theta here, as this theta here goes to 90, so you can imagine that so we want this wall to be standing upright, right? So for it to stand upright, then this angle will go to theta, and as angle theta approaches 90, you have sine of that, it will approach 1, and cos of that will approach 0. So vice versa, when sine of 0 is 0 and cos of 90 is 1. Okay, so now one would imagine that, so as we increase the wall, we should have the force of gravity being equal to the frictional force. But now remember that frictional force is given by cos of theta, and cos of 90 is 0, right? So now the frictional force will go away. That's why this object, when you increase the incline, it increases its chances of it slipping down, right? So now we need to account for why this object here is not slipping down. So you can imagine that this is difficult to understand, by the way. This is difficult to sort of comprehend, but you should imagine that you have a force acting on the plane like that, right? So how you can visualize it is someone holding the object. So the object standing on its own with glue is the same as you just standing by the wall and holding the object without glue. So this object here with glue on the wall, there is a force acting on this object that's allowing it to stay in this in this position here. So it's not because of this explanation here, but it's because of that. It's the same as you standing by the wall and holding the object like that. So you can imagine that the force of which is applied on this object here that's making it stand still like that can be divided into two components, f cos theta and f sin theta, depending on how the force is applied on the object. So you can imagine if you apply a force like this, right? So if you apply the force almost downwards, the object will move downwards. But you have to apply a force in such a way that this object will be stationary on the wall. So meaning that f sin theta will be on play because it is the vertical component of the force. And when f sin theta is equals to force of gravity, that's when this object stands still on the wall.